Okay, so we are going to do 9.4 today, and there is a worksheet. So we are going to pick up in our notes on page 14 with the nth term test for divergence. We kind of talked about this already, but we're now just giving it a name, nth term test. So basically, we have a series is going to diverge if the limit as n approaches infinity either fails to exist or is not equal to 0. So in other words, if it equals 0, there's no conclusion and we must try another test. However, if we get a limit of infinity or 2 or 3 or 100 or whatever, that's going to imply that a sub n diverges. Okay, so it's basically either equal to 0, no conclusion, and if you get anything other than 0, it has to diverge. So here we want to use the divergence test, in other words, the nth term test, to show that each of the following series is a divergent series. So I want to take the limit as n approaches infinity of 2n. Well, that's just going to be infinity, which obviously is not equal to 0. So therefore, that series diverges. Next one, we'll do the same thing. So here, we're going to take the limit. So we have 3n to the third minus 1 over n to the third plus 2n. Notice these have the same degree, and when we're approaching values increasingly large without bounds, so as n approaches infinity, we're going to get the ratio of the leading coefficients, which is 3, not equal to 0. So therefore, I'll just do b sub n diverges. Now I'm just putting in here by nth term test, even though that's what it told us to use. In the homework and later on, or in terms of the AP test, we always have to make sure that we define what test we're using in order to show that a series is either divergent or convergent. Okay, so that's the nth term test. Again, nth term test, it's easy to use if you look at a series and you can easily see that the limit as n approaches infinity is not equal to 0. If it's equal to 0, we're going to try a different test. So here's another test, the comparison test, a direct comparison. So let's say we have two series, a sub n and c sub n. If there is a convergent series c sub n, okay, so if we know that there is a series c sub n that's greater than a sub n, so in other words, if the larger one we know converges, then the smaller one converges. And then if we know there is a series c sub n that is divergent, where c sub n is smaller than a sub n, then the sum of a sub n diverges. So if the smaller one we know is a divergent series, then the bigger one also diverges. Okay, we want to use the comparison test to show that this series converges for all real x. And I put a little note in here, refer back to the table of the Maclaurin series on page 9 of the notes packet. Okay, so when we're looking at this, I'm actually going to compare You see this sum from n equals 0 to infinity of x to the n over n factorial. Okay, that's our e to the x. So let me just kind of fast forward to the page we were on. So note e to the x, which was this 1 plus x squared over 2 factorial, oops, plus x cubed over 3 factorial, so on. This converges, and you don't have to write this down, I'm just for all real x. So I'm going to use this comparison test to compare x to the 2n over n factorial squared. That has to be less than or equal to x to the nth, squared over n factorial. This right here, this is really a series for e to the x squared, which converges for all real x. Therefore, since we found a larger, right, remember here, if we know that we have a larger convergent series, then the smaller one also has to converge. So therefore, also converges. Again, and this is going to be by the comparison test. Next, we want to take a look at the ratio test. So what we're going to do is we're going to take a series, let's say a sub n, and this only works for when they have positive terms. What we want to do is we want to look at the limit as n approaches infinity of a sub n plus 1 over a sub n. So basically taking the ratio of that n plus 1 term over the nth term as n approaches infinity. And then we're going to look at our results. So if that limit is less than 1, our conclusion is the series converges. If the limit is greater than 1, the series diverges. And if we take the limit and we get equal to 1, the test is inconclusive and we have to try another test. Okay, so less than 1, the series converges. Greater than 1, the series diverges. Equal to 1, inconclusive. So let's take a look at an example of how we would use this. Okay, so I want to take the limit as n approaches infinity. So I'm going to take the n plus 1 term. So that's going to be n plus 1 cubed over 3 to the n plus 1 plus 1 all over n cubed over 3 to the n plus 1, so the nth term. Okay, so now I'm going to rewrite this. So I have n plus 1, it's all algebra from here basically, and then evaluating our limit. So we're going to multiply by 3 to the n plus 1 over n cubed. Okay, so now what do we have? Well, let's take a look. I have n plus 1 cubed and n cubed. So I'm just going to put this all as n plus 1 over n to the third power times I have 3 to the n plus 1. And then in the denominator, if I take out, I could do that 3 times 3 to the n plus 1. Now, if I look at this, this is going to go to 1. So let me just kind of write this part. So it's 3 to the n plus 1 over 3 times 3 to the n plus 1. So if I divide the top and the bottom, or how about look at it this way, let's multiply everything times 1 over 3 to the n. So that's going to give me 1 plus 1 over 3 to the n. And then in the denominator is going to be 3 plus 1 over 3 to the n. So as n goes to infinity, this will go to 0, this will go to 0, so I get 1/3, which is less than 1. Therefore, the series converges. And again, we use the ratio test. Okay, so now for example 3, we want to determine the convergence or divergence of the series, and we're going to identify the test or tests that we used. Okay, so basically, here's what we know so far. Geometric series, all we need to do is basically show that if it's a geometric series, if r is less than 1, it's going to converge. Otherwise, it's going to diverge. Nth term test is basically to tell if it diverges. In other words, if the limit does not equal to 0, then it diverges. The comparison test, this is when we compare, so we compare a series to something we know converges or know diverges, and that's how we will determine it. And then the ratio test is the one we just did. That's the n plus 1 term over the nth term, and we want to see if we can show that is less than 1. Okay, so for A, again, so geometric series, we're looking for that common ratio. Anything with a factorial is not going to be a geometric series. I can look at this, I could try to show the nth term test, comparison test, ratio test. I think it might be good just to practice the ratio test a few times, so let's try that for A. So we're going to do the limit as n approaches infinity. So we're going to do the 2 to the n plus 1 over n plus 1 factorial. Now I'm just going to automatically multiply by the reciprocal, right? Because we're just going to divide by 2 to the n over n factorial. So I'm going to write that as multiplying by n factorial over 2 to the n. Now, just a quick kind of side note, because I don't know how much practice you've had with factorials, but keep in mind, right, n factorial is really n, right, times n minus 1, times n minus 2, times ... all the way till you get to 3 times 2 times 1. So if I have n plus 1 factorial, that's going to be n plus 1 times n minus 1 times n minus 2, ... all the way down. So if I put, let's say, an n factorial divided by an n plus 1 factorial, just as an example, I can just rewrite n plus 1 factorial as n plus 1 times n factorial, right? Because all of this is n factorial, which would allow me to simplify to make it just 1 over n plus 1. Okay, it's kind of like if you had 8 factorial over 7 factorial, or vice versa. You could say, oh, that's 8 times 7 factorial, which would cancel the 7 factorial at the bottom. So that's kind of the approach I want to do here. Let's see, actually I'll just write underneath it. So n factorial. Let's see, first of all, I have 2 to the n plus 1, so I'm going to write that as 2 to the n times 2 times n factorial. And then in the denominator, I'm going to have n plus 1 times n factorial times 2 to the n. Again, the reason I rewrote the 2 to the n plus 1 is so that I could easily see what's going to cancel for me here. So these are going to cancel. These are going to cancel. And what am I left with? I'm left with the limit as n approaches infinity of 2 over n plus 1, which equals 0. And we use the ratio test. So remember, according to the ratio test, if we can show that the limit is less than 1, our conclusion is the series converges. So therefore, the series converges by the ratio test. Okay. Next one, and again, there could be more than one way to prove this. This one has n factorial over e to the n. Okay, so let's try the ratio test again. So we have n plus 1 factorial over e to the n plus 1. Then I'm going to multiply by the reciprocal, so that's going to be e to the n over n factorial. Again, if you want to pause it here, just go ahead and try it on your own, see if you get the same thing as me. Again, I'm going to rewrite the n plus 1 factorial. I'm going to make that n plus 1 times n factorial e to the n over e to the n times e times n factorial. And let's see what cancels. The n factorials will cancel. The e to the n will cancel. So I'm left with n plus 1 over e, which that's going to approach infinity, which is definitely greater than 1. Therefore, the series diverges by the ratio test. Okay, next one, we have n times natural log of n over 2 to the n. Let's do this. Also, let's try another ratio test as practice. So I have n plus 1 times natural log of n plus 1 over 2 to the n plus 1 times, so that's going to be 2 to the n times the reciprocal, so n natural log of n. Okay, so we have limit as n approaches infinity. Now, I am going to group together, let's see, whoops, did not mean to do that. I want to do n plus 1 over n, because if I group that together, I can easily see, right? N plus 1 over n, that's going to go to 1. Let me also group together my natural logs. So if I do the natural log of n plus 1 over the natural log of n, that also will approach 1. So now let's take a look at my 2 to the n and my 2 to the n plus 1. So I'm going to rewrite the denominator, that 2 to the n times 2. And so this will go to 1, this will go to 1, the 2 to the n's will cancel, and so I get a half, which is less than 1. Therefore, the series converges by the ratio test. Okay, next one, we have D. All right, well, D, if you recognize, this is really 1/3. You can also write that as 1/3 to the n. That's a geometric series, right? So R is equal to 1/3, right? Which is less than 1. Therefore, the series converges because it's a geometric series with the absolute value of r less than 1. Okay. These are just 2 more examples here. Again, same directions basically. And again, you can choose. If you can compare it to something that we know, or you can prove it with the nth term test, or if you can identify it's geometric, or you can use the ratio test. Okay, well, when I'm looking at this one, I can see 3 to the n over 5 to the n also would be 3 over 5 to the n, which would be a geometric series. This geometric series converges, right? Since r is less than 1. And then if we compare 3/5 to the n compared to this function, this has to be greater than or equal to the function that the series that we are given. So therefore, remember the comparison test. If I can identify a larger, right, one that we know converges, then the smaller one must converge. That's how the comparison test looks. So I identified a geometric series that converges, and since it's greater than or equal to 3 to the n over 5 to the n plus 1, by comparison test, this series also converges. Okay. Again, this is not the only way you could have done. You could have also tried the ratio test if you wanted to for this. Okay, this one has a factorial, so I know it can't be geometric. I'm going to go to the ratio test. First thing, I'm going to just think of this as n factorial over e to the n. So when I'm writing this out, I have n plus 1 factorial over e to the n plus 1. And then I'm going to multiply by the reciprocal, e to the n over n factorial. So I'm going to have n plus 1 times n factorial times e to the n over, and then I'm going to write that as e to the n times e times n factorial. Let's take a look at what we can cancel. N factorials, e to the n. So we had limit as n approaches infinity of n plus 1 over e, which equals infinity, which is greater than 1. Therefore, the series diverges by the ratio test.